Hello, good morning all. In today's class, we'll discuss Coriolis component of acceleration. So whenever slider is moving in intermediate links and it is connected to crank, then it has two relative motion. One is with respect to crank, that is it has a rotary motion, and second is with respect to this intermediate member, it has a sliding motion. So we need to identify when these two motions are going to happen for intermediate slider, then there is one component which is going to exist for that relative motion, and that component is nothing but your Coriolis component of acceleration. Okay. So for Coriolis component, one is having a rotary motion and second is having sliding motion. So one body with respect to that one link is having rotary motion with respect to that slider, whereas second link is having sliding motion with respect to that slider. So let's say point A and B we have, that B point is on link, that is link 3. Slider we are saying A is a fixed point, that is on link 2. Okay. And B and A are coincident at that particular instant. So link 2 is having constant angular velocity omega 2, and it is moving from OP1 to OP1 dash, OP to OP1, and slider B moves from B to B2. Okay. So what we have, B2 to A1, this motion we are tracing as a rotary motion for link 2, and A1 to B1 motion, that is for this slider motion, we are tracing as a outward velocity sliding motion. Okay. So there is a component we need to draw due to this relative movement of this slider along rotary direction and sliding direction, and that is your acceleration component, which is perpendicular to link 2. Okay. So to trace that Coriolis component of accelerations, what we have velocity of that two correlative points, that is B and A, and its angular velocity on which that slider is moving or slider is sliding. That is your omega. So your Coriolis component of acceleration will be A 2 will be omega 2. That is the Coriolis component of accelerations that we need to understand. Okay. Now there are four types of components we need to plot depending upon the direction of rotation. Suppose say if that intermediate link is moving in anti-clockwise direction, then Coriolis component will exist towards left side. If it is moving in clockwise direction, it is moving towards right side. At the same time, we have to consider sliding moment, whether that slider is moving in upward direction or downward direction. So if slider is moving in upward direction in both the cases, then the Coriolis component of motion will be in the direction of rotation for that link, and it is in perpendicular to that link. So the component will be towards left side because your link is moving in anti-clockwise direction, and it is perpendicular to this link. That means it is 2b into omega. Similarly, it is 2 velocity of that particular outward velocity of slider into omega of that link where that slider is sliding. Similarly, if you look at the inward velocity of v, that is whenever slider is sliding in downward direction, at that time this component will exist in opposite direction. That means if your link is moving in anti-clockwise direction, Coriolis component will be right side. If link is moving in clockwise direction, your Coriolis component will be on left side. So this is the overall direction of rotations we need to consider, and uh, we need to find out the where to locate the Coriolis component, whether at left side or right side, depending upon the rotation of intermediate link. That is completely depending upon your velocity of slider and rotation of that link. Okay. Now, next part is just we'll take one example, and based on that example, we'll try to understand how to plot that Coriolis component of acceleration. Okay. So we have this crank and slotted lever mechanism. Crank rotates with uniform speed of 60 RPM. The speed of crank is given. This is the crank OB. Sorry, AB is the crank. OC is your intermediate link. CD is output link, that is connected to uh, plunger. Okay. Line of stroke is given. Line of stroke, that is line of stroke of ram is perpendicular to OA, and we need to determine the acceleration and velocity for point D, that is for plunger D. So we can first find out RPM is given. We need to find out first angular velocity of your crank OB. So what is angular velocity of that crank AB? 2 pi upon 60. So it is 2 pi into 60 upon 66.28 radian per second. So first we need to find out velocity of crank. So velocity is R into omega. So what we have? We have R, that is radius 6.28. Radius is 0.1 because AB length is 100 mm, and omega is 6.28. So if you multiply by that radius into omega, we have velocity of that slider B, which is 0.628 meter per second. Next, to plot that component, all these components will follow this process. Okay. So first we need to take some scale. We'll take scale 1:5. Okay. So 1 centimeter is equal to this distance is 1 centimeter is equal to 20 mm we can take. Okay. So first we will draw that part of OC. OC is given 400 mm, AB is given 100 mm, OC is OA is 250 and CD is 150. So first we'll draw this line of 450 mm. Okay. So 1 centimeter is equal to 50 mm. That is our scale. So just we'll first draw two parallel lines having distance of 9 centimeter. Okay. Then we'll locate one AB OA line. OA is given 250 mm. That is, this line will be of 5 centimeter. Then we will mark that crank AB 100 mm means 2 centimeter at an angle of 120 degree, and then we will cut that OE OC distance. So we have OC part 400 mm, that means 8 centimeter, and we have this CD part 150 mm, that is 3 centimeter. So take C as a center and cut that center on that horizontal line. You will get CD position of stator. Okay. Now to locate that velocity part, so we have fixed point O and A, that is A dash OA we can locate. Then velocity is perpendicular to motion as your crank rotates in clockwise direction. This will be velocity component. So what we have velocity 0.628 meter per second. V is equal to R omega. That is already we have calculated. So just draw this line, perpendicular line of 1 centimeter is equal to 0.1 meter per second. That is 6.2 centimeter. After this, we have to draw again second line for AB. Okay. So this AB line, that is A and B is your velocity component. Then we'll draw second perpendicular for this OE line. B and E. Just look at the part. B is point on crank, E is point on stator that we are considering. So what we are drawing? We are drawing one parallel line for B and E. Okay. And there is one more line for a perpendicular line to tangential to motion. That means velocity component is tangential to motion means again there is one more perpendicular line for OE. So this is one perpendicular for that part. So this perpendicular line and this parallel line will define orientation of E. So what we have, B point is on stator, B point is on crank, E point is on stator. So in this way we can locate point E. Okay. So this is the arrangement. Then extend that part by applying equation OC upon OE is equal to small OC upon OE. So if you put the length OC 400, OE 320. Similarly, this OE distance is 460. Sorry, 46. So OC will have 57.5. So just extend that line up to 57.5 mm. Okay. So you get point C. Then for C and D, just draw one perpendicular line in this direction and then one horizontal line. So after plotting perpendicular and horizontal line, because slider is moving in horizontal direction, you get point D. So just connect D and C and D and point O. So in this way, we are getting that all the velocities for all the points. Okay. So our question is, you know, to determine velocity of D. So just measure that distance multiply by scale, you will get velocity. So we have this velocity of D 6.35 into 10, that is 63. Scale is 1 centimeter is equal to 0.1 meter per second, or you can say 10 centimeter. So 6.35 into 10 is 63.5 centimeter per second, or 0.635 meter per second. Okay. By putting this part, can measure the velocity of slider, and we have all these velocity for all the component. Velocity of point E, just measure this distance 4.6 into 0.1, 0.46. Velocity of B, we have measured that B part also. So that distance we have, then we can measure the velocity of C part. Okay. So by considering all these intermediate velocities, we need to find out the acceleration values. Okay. So next part is just look at the acceleration diagram. Okay. Now what we have discussed velocity. There will be two component, normal and tangential component of acceleration. So normal component will be parallel to line, tangential will be perpendicular to line. Okay. So to just calculate the Coriolis component of acceleration, we should have omega B and velocity of B. So velocity of B already we have found out. So velocity of B is around 0.42 centimeter per second. And angular velocity that we can calculate. Angular velocity is velocity of E upon OE into VB. So this part is 1.2075 meter per second square. Okay. Now to plot that acceleration component again, just look at that A dash O dash point. Then B dash is in upward direction, locate B in downward direction. By finding that normal acceleration value is 3.94 meter per second square. Again, you can take scale. You can take scale 1 centimeter is equal to 1 meter per second square. So this line will be of 3.94 meter per second square. Okay. Then next is a B dash to Y dash, that will be perpendicular to OC part. Okay. Then again will be normal component which you need to draw parallel to BO. Okay. Then after that we have to draw tangential component for that BO part. Okay. And then from Y dash we have to draw one parallel line to OC that will intersect the perpendicular line. Okay. And this intersections of perpendicular line of BO and perpendicular line of EB will define the orientation of E. So just connect E part and O dash part. Okay. So again extend that part OC upon O is equal to OC dash upon O dash E dash. So we have O dash E dash value 2.75. Extend that line. Again normal component we need to plot. So normal component will be V square upon R. So that will be 0.216 meter per second square. Okay. So that value we have. Then from C dash we need to draw C dash to Z dash line, that is to determine the position of D. So that will be one perpendicular line. Okay. So one parallel line and one perpendicular line we need to draw for CD line. Okay. And then we have to draw a horizontal line to define the point D dash. So if we join that part, we get D dash part. So just connect D dash and D dash. So in this way, we can complete all these acceleration part. And finally, it has been asked to measure acceleration of slider. So just measure O dash D dash scale into scale. So 3.4 point to 0.5, we have 1.725 meter per second square. So we can determine the Coriolis component of acceleration for this intermediate slider position. So this is all about how to plot Coriolis component of acceleration for slider, which is mounting on intermediate link. Okay, stop here.